In question number 21, an inductor resistor's battery circuit is switched on at t equal to 0. If the EMF of the battery is V0, find the work done by the battery in one time constant after the switch is closed. So we know that at t equal to 0 when the switch is closed, the current at any time t is given by V0 by R into 1 minus e raised to the power minus R by L into t. Now we have to find out what is the charge that crossed this battery in a one time constant. So Q is equal to integration of I dt, and the limit of time varies from 0 to L by R. So if I integrate this function with respect to time and substitute the limits, then it comes out to be L into V0 divided by E into R square. So the work done by the battery is equal to Q into V0. So it comes out to be L into V0 square divided by E into R square. So option 2 is the correct answer. Let's move to question number 22. In question number 22, maximum power developed across variable resistance R in the circuit shown in the figure is. So if I make the equivalent of these two cells, then it can be represented as this is equivalent, this is internal resistance R equivalent, this is equivalent, and here is the variable resistor R. So if I find out the R equivalent, then it comes out to be 4 ohm because these two are in parallel. And for the E equivalent, we apply the formula E equivalent divided by R equivalent is equal to 10 by 5 E1 by R1 plus 10 by 20, that is E2 by R2. So on substituting the value of R equivalent is equal to 4 and solving for equivalent, it comes out to be 10 volt. So this value is 10 volt and this value is 4 ohm. Now from the maximum power transfer theorem, we know that the value of this variable resistor must be equal to 4 ohm in order to have maximum power in this resistor. So the maximum power is given by current through this resistor. So the current will be 10 volt divided by total resistance is 8. So I square into R. So the value of R is 4. So in solving this, it comes out to be 6.25 watt. So option 2 is the correct answer. Let's move to question number 23. In question number 23, a uniform wire of resistance 100 ohm is shaped into a regular hexagon. The equivalent resistance between any two corners has the minimum value given by. So let's understand the situation. A uniform wire is made into a regular hexagon. So if the total resistance is 100 ohm, then the resistance of let this branch is 100 by 6, or it is equal to 50 by 3 ohm. Now if one of the point is this, and we have to consider a second point such that the resistance between these 2 points must be minimum of this given regular hexagon. So we know that 1 by R equivalent is equal to 1 by R1 plus 1 by R2 in case of parallel arrangement. And the value of this R equivalent is minimum to both of R1 and R2. So if I consider my first point, so if I consider my other point at this point, then the value of R1 becomes R and the value of R2 becomes 5R. Then this 5R and this R would be in parallel. So the resistance would be less than R. But if I consider my second point to be at this position or at this position, then R1 value is either 2R or 3R. So in that case, the R equivalent would not be less than capital R. So this is the right situation. I am considering these 2 points as this and this. So the R equivalent for this combination is given by 1 by R plus 1 by 5R. So on solving, the value of R equivalent comes out to be 5R by 6. On substituting 5 by 6 into value of R, that is 50 by 3. So on solving, it comes out to be 125 by 9 ohm. So option 2 is the correct answer. Let's move to question number 24. In question number 24, the linear charge density on a ring of radius r is varying with theta as lambda is equal to lambda naught cos theta by 2. Then on any point along z axis, we have to choose the validity of given options. So if I draw the charge on this, then when theta varies from 0 to pi, then this would be positive, this part would be positive, and when theta varies from pi to 2 pi, then this part would be negative. So we can see that the distribution of charge on this quadrant and on this quadrant is symmetric, and the distribution of charge on this quadrant as well as in this quadrant is symmetric. So if I find out what is the net direction of the dipole moment due to these charges, the net direction of the dipole moment will come in this direction, that is along j cap. So let's choose the options for the given point which lies on the z axis. So we know that the total charge on this ring is 0. So the electric potential at any point on the z axis would always be 0. So option 1 and 2 may be correct. But if I consider then the direction of the dipole moment is along positive y-axis, then we can say that this point lie on the equatorial point. Then this point is the equatorial point for the dipole, and the direction of the electric field at that point would be along negative y direction. So we can say that E dot k is 0 and E dot j is not equal to 0. So option 1 is the correct answer. Let's move to question number 25. In question number 25, two plates of a capacitor of capacity C are given charges Q and 2Q. This capacitor is connected across a resistance R as shown. Find the charge on plate 1 at time t after the switch is closed. So just before closing the switch, if I make the arrangement, these are two plates of capacitor. The total charge on the plate of capacitor is 3Q. So the charges on the outside is 3Q by 2 and 3Q by 2. So here it is the positive plate plus Q by 2, and here it is minus Q by 2. So initially the charge on the inside surface is negative, and when they are connected by a resistor at t equal to 0, then the charge on this plate is given as Q1 at any time t as 3Q by 2. This is the charge on this plate, and the charge on this plate at any time t is given as minus Q by 2 into e raised to the power minus t by RC. So option 3 is the correct answer. Let's move to question number 26.